हेलो चिल्ड्रन, वेलकम टू टीच टैगर्स। स्वागत है आप सबका टीच टैगर्स में एंड दिस इज वंशी, योर केमिस्ट्री मेंटर। तो चिल्ड्रन, वी आर इनटू लेक्चर नंबर 3 of this very interesting chapter, aromatic compounds. So before we begin our day, let's have a quick recap on what we have studied in the last class. Guys, we have seen what are electrophilic aromatic substitution reactions. We have seen some examples of electrophilic aromatic substitution reactions, right? And what is that we are going to study in today's session? Today we have seen electrophilic aromatic substitution reactions, and we have just discussed the mechanism, but I haven't told you the electrophiles in particular. Say in chlorination or in nitration or sulfonation, what is the electrophile? I didn't tell you. I have just shown you the mechanism, taking electrophile as E plus in the lecture number 2. Am I right? So in this session, we are going to study in detail every reaction of EA. Yes, 6 types I told you. All those 6 we are going to study, and we are going to see what are the electrophiles in each case. So guys, let us first begin with electrophilic chlorination of benzene. This is what we have. I'm sorry. So this is what we have, guys. We have benzene, am I right? And I treat it with chlorine. The reaction is so slow here. In fact, it doesn't take place. The rate of the reaction is very slow. So what I do, I told you, Lewis acid accelerates the rate of EAS reactions. So I have taken here AlCl3. Then you are going to get the product. Am I right? Is this clear? The question is, what is the electrophile in this reaction? Right? Let us see, guys. Now you see, if you can see here, this chlorine is not a strong electrophile. Now what is that we are going to add? We are going to add an Lewis acid. What does it do? It activates the electrophile. Right? Like how? Let us see. I have taken this AlCl3. This is electron deficient compound with aluminium having only 6 electrons on the central atom aluminium, right? So it acts as electron pair acceptor. Now you can see chlorine has a lone pair electron, and hence it tries to donate the electron. Is that clear? So what is that we are going to have? Can you tell me? This is chlorine. This chlorine, when it donates electron, it has got positive charge, and aluminium has what charge here? Negative. This is what we have. Am I right? Now you see the bond wasn't polarized in the first case. Now this chlorine with positive charge will try to pull the electron cloud towards its side. Because it is having a positive charge, it cannot bear the positive charge. Am I right, guys? So what does it do? When it tries to pull the electron cloud from this chlorine, we have a partial positive charge on this chlorine atom now. Why? Because this chlorine is more electronegative. Why more electronegative? Because it has got a positive charge on it. Right? Now guys, you see, as soon as this chlorine sees this benzene ring, which has got high electron cloud density, then what does it do? This chlorine will give electron to this chlorine atom. Right? So what do you have, guys? You have got Cl plus. This chlorine atom has donated its electron. It gets Cl plus you have AlCl4 minus. Am I right? Guys, you see, you can't just write Cl to giving rise to Cl plus and Cl minus. It's a weak, that doesn't happen under normal condition. So we say chlorine is a weak electrophile. Now what did I do? I have just added a Lewis acid. What was that? AlCl3. What does it do? It activates the electrophile. How did it activate? It has first polarized the bond, right? And then it takes away the electron from this chlorine, giving rise to AlCl4 minus Cl plus. Now this Cl4 plus acts as electrophile. Now why did this chlorine give electron? Because it knows it can attack the benzene ring. Right? So this is the electrophile. We'll call this as chloronium ion. Am I right, guys? this chloronium ion acts as the electrophile during chlorination, right? So how did this reaction happen? Because of this catalyst AlCl3. And I told you step 2 and step 3 are the same as we have seen in the lecture number 2, right guys? So I'll just show you this particular case and the remaining you have to understand on your, you have to try to write on your own those 2 steps, right guys? So I'll show you, this is the first step. I hope you have understood. This is how the bond has got polarized. Now I'll show you step 2 and step 3. The first step is the formation of electrophile. What was the electrophile guys? It is chloronium and we have got the Cl plus. What is step number 2? Attack of electrophile by the pi electron of the benzene ring. So this chlorine atom accepts the electron, pi electron cloud from benzene ring. One of the carbon gets positive. This is hydrogen which is already there on the benzene ring, and this is the chlorine atom. Am I right? This is called arenium carbocation, which is already resonance stabilized. I have already told you, right? Now this next step guys. The next step, I have taken AlCl4 minus, which is going to act as a base. What does it do? It accepts this proton, right? Now, when this carbon atom gains electron from hydrogen, hydrogen is last as H plus. Am I right or wrong? What is the driving force for this reaction? The driving force for this reaction is when deprotonation takes place, when hydrogen separates out as H plus, this carbon gets negative charge, and this positive can form a bond. You have chlorine. This H plus, however, reacts with AlCl4 minus, you are going to get HCl plus AlCl3. You can see AlCl3 is regenerated again, so catalytic amount is enough to accelerate the rate of this reaction. Is this clear? Step 2, step 3 are the same for every reaction. Only first step, the generation of electrophile, is what we are going to discuss in each and every reaction. 6 reactions of EAS. So guys, what is the electrophile in case of chlorination? It is chloronium. Em is the suffix I told you that we add for positively charged present on a non-metal, right? Ammonium, chloronium, bromonium, and so on. Is this point understood? Now guys, I have a small question for you, illustration for you. I have given a reaction here. The reaction shown below depicts an electrophilic aromatic substitution. So you have an electrophilic aromatic substitution here. What is the electrophile? And determine the product of this reaction. Pause the video and just go through it. Right? So, what is the product? Please make a try. Hope you people have paused and done the problem. Now see what do I do. Guys, I have this ClBr. Am I right? Now tell me whether the bond is polarized or not polarized. Let us see. I guess you people know chlorine is the 4th most electronegative element in the periodic table. Fluorine the most. Next comes oxygen. Next nitrogen and chlorine. Am I right? In fact, both nitrogen and chlorine have same value in Pauling's electronegativity scale. But because of the large size of chlorine, it loses to nitrogen. Anyways, what is the point here? Chlorine is more electronegative than bromine. Hence, the covalent bond is polarized. So, chlorine is to get partial negative and bromine the partial positive. Am I right? So, this is the, unsymmetrical reagent that I have here. Guys, I also have AlCl3 which is going to act as the, Lewis acid. So, I have AlCl3 here. AlCl3, aluminium is electron deficient. It tries to accept electron cloud. Am I right? It attacks a site of high electron cloud density. Can this attack positive charge? No. This is already an electron deficient. So, this step is not possible. Why it couldn't do it? It couldn't do it because aluminium is electron deficient and electron deficient site species attacks a site of high electron cloud density. So what does this do? Now this aluminium tries for chlorine. Why? Now chlorine has electron rich side. Therefore, this aluminium approaches this chlorine, not bromine. So guys, how do I write the reaction? You see, AlCl3 plus this is chlorine and this is bromine. This is partial positive, this is partial negative. Am I right? So aluminium is going to accept electron from whom? From chlorine, because it has lone pair. Right guys? Now see what happens. You have got this. Chlorine has got positive charge. Now guys, tell me, can chlorine bear a positive charge? No, it pulls away the electron from bromine, hence it results in high positive charge. Clear guys? Now, in the presence of benzene, this bromine donates an electron to chlorine. So what is that you are going to get? When bromine donates an electron, you are going to get Br plus AlCl4. This 3 here, 1 chlorine. This positive charge is last because this chlorine atom is gaining electron from bromine. So you have got this. Bromonium ion is the electrophile here. Am I right? Check it out. So the first question here is, what is the electrophile? We have bromonium ion. Am I right? So determine the product of this reaction. So obviously, what would happen, guys? So when this is hydrogen, when you attack this with bromine in the presence of AlCl3, after step 2 and step 3, you would be getting this. So bromobenzene is the product form, guys. Very interesting question. Am I right? Just see. This is the electrophile here. Hope you have understood this. This was the question given in your earlier entrance exam. Now I have one more question, guys. What is the question? Just see. We have here naphthalene. I shown you in lecture number 1 about types of benzonides. Fused benzene rings you have, right? This is naphthalene, 2 benzene ring fused together. Now the question is, if I subject this to chlorination, if you take a single benzene ring, then I told you all the positions of the hydrogens are same because benzene is a perfect and pure example of a hexagon. Anywhere you can substitute, you are going to get only one mono halogen derivative. But here, guys, that's not the same. The position of all the atoms is not same here. So the question is, theoretically, I am not sure whether you are going to get 1 or 2. That depends upon the mechanism of the reaction. Once we go through the mechanism, depending upon the activation energy of the intermediate, we will decide what is the major product. But theoretically, how many mono-substituted naphthalene derivatives can be formed in this reaction? Can you people guess? Please make a try. Anyways, I'll try to explain this. So guys, I told you there are many Lewis acids that you can take, right? So what is the Lewis acid that is considered here? Just see, we have taken FeCl3. Earlier case I have taken AlCl3. I told you can take ZnCl2, FeCl3. Am I right? So guys, I have this naphthalene. Okay, and this is what we have. Now I treat it with chlorine and you have this Lewis acid. Now hydrogen of this naphthalene has to be substituted with chlorine. How many ways can you do it? Guys, you see what do I do? This is the ring I have. Am I right? Now what can I do? Can I keep one chlorine here as the product? If this hydrogen is substituted by this chlorine, this is one of the product that you can get. But guys, if you write the same compound like this, is this one and the same? Yes or no? It is same. So whether you write chlorine here or here or here or here, it is same. So I am not considering all of them, only one of this product. Second, I see here. Guys, see what did I do? This is what I have. This is one chlorine atom, right? This is the another position. Can you see? Now if I do this, both are same. Am I right or wrong? Is this clear? Or guys, if I add another chlorine atom here, say or, I write this here. They are one and the same. So you are going to get theoretically only two species here. And we are going to name them. Because many times such questions have been asked. Right? So how do you name them? Guys, I'll just rub this. You are going to have theoretically only two. If you have here or here or here, it is same. If you have here or here or here, here and here, it is same. So guys, now this position we call it as alpha substituted with this fused ring. This is the fusion, this is the carbon atoms that have been fused, and this position is called alpha substituted halogen derivative we call. Now sir, what is this? This is the fused ring carbons, right? This was first carbon, this is the second carbon atom, numbering. So we call this as beta substituted. Am I right? So this is with respect to this, we call this as alpha and this as beta. Remember, we'll follow this nomenclature many times. This is not IUPAC accepted. We have called this as 1 chloro-naphthalene like that. This is 2. Anyways, this is alpha substituted and this is beta substituted. You are going to have two monohalogen derivatives theoretically. Is that understood? Yes or no? Check it out. Okay guys. Now let us go for the next EAS reaction. I have told you we are going to discuss two types of halogenation. One was chlorination and the other bromination. Right guys? Now we have seen the mechanism. Bromination is in fact very slow. Chlorine, of course, if you have phenol, chlorination can take place on its own. Say you have this. These are the experimental observations, guys. You take chlorine. Now, this reaction can take place. Even if you don't add AlCl3, the reaction can proceed. But bromination is very difficult. Here, in this case, bromination requires a catalyst. So, what do? Yes, I'll rub this. I'm considering this. Why phenol reacts directly with chlorine? Because it has got ring activating group. What is that? OH. We'll discuss that in the later session. Now, I told you the reaction would be still slower than Cl2. Right? Now, what do? I'll add a Lewis acid. Do not take FeCl3. Go for FeBr3. Now, what does this Lewis acid do? It activates the electrophile. What was that weak electrophile you have? You have got bromine. And this was FeBr3. Bromine, as usual, like chlorine, it has got lone pair, it donates. Now see what happens. Bromine, this bromine has donated, it has got positive, iron has got negative charge. Now see, the bond was non-polar. Now when you add a catalytic amount of FeBr3, this bromine has become more electronegative and it will try to pull the electron cloud towards its side. As a result, there is a partial positive charge developed. Now, as soon as this bromine sees this benzene ring and it knows that it can attack this, it will donate its electron to this bromine. When positively charged bromine atom gains this electron, it becomes neutral. There is still a negative charge on iron. You have got FeBr4 minus. Plus, bromine has lost electron, you are going to get Br plus. We call this as bromonium ion. So, what was the electrophile in chlorination? It was chloronium. This is bromonium ion. And the product is same. Step 2 and step 3 would be same like in case of chlorination. Only difference is, instead of chlorine, you will have Br plus. Right? Is that point clear, all of you? So, electrophilic bromination of, benzene, right? What is that you are going to get? You are going to get bromobenzene. Am I right? So, in the next step, Br plus would attack this benzene ring, resulting in this. So, the electrophile is bromonium ion. Clear all of you? Now guys, let's go for the nitration. I told you what is nitration already. Right, let me explain this. I have got a benzene. I treat it with the HNO3 and H2SO4 in 1:1 ratio. We call this mixture of concentrated HNO3 and H2SO4 in 1:1 ratio. We call it as nitration mixture. Then you will have this nitrobenzene. Guys, addition of this NO2 group is called nitration. The nitration product of benzene is nitrobenzene, guys. Is that point clear, all of you? Now see, what do I do here? What's the deal with nitrobenzene? How does this reaction take place? Now, let us see what is the electrophile here. Okay, let's see. Guys, HNO3 and H2SO4 I have taken in 1:1 ratio. Let's see what is the structure of nitric acid. This is what the structure of nitric acid is. Plus, you have this. Now you tell me, between H2SO4, sulfuric acid, and HNO3, which is the strongest acid? Obviously sulfuric acid. What does an acid do? It donates a proton. To whom does it donate? To nitric acid. Am I right? So now you see what is going to happen. You have got this lone pair. And since this is a stronger acid than HNO3, what does it do? It will donate one H plus to this. So there is a protonation from sulfuric acid to HNO3. Am I right? So what is that you are going to get? When H2SO4 loses a proton, you are going to get HSO4 minus. Am I right, guys? Right? Now what do you get? This is N double bond. This is O. Right? So when you know here, when nitrogen forms 4 bonds, it will have a formal charge of +1. Oxygen, when it forms 1 bond, it will have a formal charge of -1. You people know it. Now I have minus here, I have plus. Now when this donates a proton, you are going to get OH2 plus. Now, can oxygen bear a positive charge? No, it cannot. So what does it do, guys? It will accept this electron from nitrogen. So you have got H2O plus. Nitrogen has lost electron to oxygen. What charge will it get? Positive. Can it bear a positive charge? No. Then who is going to help it? This oxygen is negatively charged. It is so rich. So as soon as this nitrogen donates an electron to oxygen, this oxygen will donate electron to this nitrogen. So what is that you are going to get? This is N double bond O. And this oxygen has donated electron to this nitrogen. We have this. There is still a positive charge on nitrogen. It has donated 1 electron and accepted 1 electron. So, no charge because of this electron donation and acceptance. One it is donated, one it is accepting. But now, there is already a positive charge on this. So, I have written here NO2. This is the electrophile. We call this as nitronium ion. Nitronium ion is the electrophile. By the way, I have a simple question. As what is the role of HNO3 in nitration mixture? Nitric acid, does it act as an acid or a base here? Just check it out. Suppose I ask you, what is the role of nitric acid in nitration mixture? Does it act as an acid or a base? Guys, can you see here? It is accepting a proton from sulfuric acid. Hence, it is going to act as a Bronsted base. What is a Bronsted base? Proton acceptor. Did I tell you about acid bases in the GOC? Yes. So, here it is accepting a proton. Proton acceptor is called Bronsted base. So, HNO3 is acting as a base here. Am I right? What is the electrophile generated here? Nitronium ion. And one word of caution here. How does this nitronium ion attack this benzene ring? This is NO2 plus I have written here. Now guys, can it directly make a bond? I told you any atom belonging to second period can never ever violate octet's rule. It can never happen. Then sir, what does it do? See, as soon as this has got a positive charge, it will attack this benzene ring. But in this process, what is happening? Just see. Say this carbon has donated electron to this, you have a positive charge on this carbon. And there is a negative charge on this carbon which is going to donate electron to nitrogen. But nitrogen cannot form 5 bonds. Then what does it do? It will donate one electron to oxygen. Then see what happens. When this oxygen gains electron, you are going to get O minus. Am I right, guys? And here you have double bond O. This is what we have. Whenever nitrogen forms 4 bonds, I already told you it is going to have a formal charge of +1. So there is still a plus charge on nitrogen. It has donated one electron to oxygen and accepted one species. Nitronium ion is highly reactive species. Powerful electrophile here. Right? So this is the step 1 is the formation of nitronium ion, which is the electrophile. And step 2 is the formation of this rhenium carbocation. I need not remember, I remind you every now and then there is a proton here. So this is the next step. What is the next step, guys? You have got HSO4 minus. Where? Here. Am I right? How did it HSO4 minus? Because after donating a proton, you have got this. Now see what happens. This HSO4 minus grabs this proton and you get H2SO4. Sir, what is the driving force? The driving force for this reaction is the formation of stable aromatic ring here. What is that? When this carbon accepts this electron from hydrogen, that means when deprotonation takes place, carbon gets negative charge and both of them would form a covalent bond. This is what we have. Of course, NO2 we have. Is this point understood? Just check it out. This nitronium ion is the electrophile in sulfonation, in nitration of benzene. Just check it out. This is the nitronium and how it is formed. Is this clear? Now guys, we'll see the, can you tell me what is the role of, acid here in this nitration? I didn't use any Lewis acid. I did not take AlCl3, nor did I take FeCl3 or FeCl3. What did I do? I have added H2SO4. Sir, what is the role of that? Guys, the role of this acid H2SO4 is to activate the electrophile. HNO3 right, undergoes protonation, right? Who protonates it? Sulfuric acid, and hence you will get NO2 plus. So unlike in chlorination and bromination, which I have used Lewis acid to activate the electrophile, in this reaction the electrophile gets activated by the acid. Am I right? Next guys, I have sulfonation. See what is the reaction. First try to write the reaction and then I'll explain the mechanism. So children, now we have sulfonation of benzene. We have already studied what is sulfonation, right? Benzene reacts with concentrated sulfuric acid and SO3, or we can say fuming sulfuric acid, to give benzene sulfonic acid. This is benzene sulfonic acid, right? This process is known as sulfonation of benzene. Okay, so let me remind you, unlike all these reactions, the earlier reactions that we have studied, this sulfonation is reversible in nature. Why? We'll discuss once we finish this sulfonation process. Right guys? So this process of adding SO3H group onto the benzene ring, hydrogen of benzene is replaced by SO3H. This we call it as sulfonation. The product formed in this reaction is benzene sulfonic acid. This is sulfonic acid group and we call this as benzene sulfonic acid. Am I right? Now the question is, what is the electrophile in this reaction? Second, Did we use any Lewis acid here? If not, what is the species that is activating the electrophile? Am I right? So guys, let us come to the mechanism of the reaction. The electrophile in this reaction is sulfur trioxide. Now, very important, we pass sulfur trioxide into the reaction mixture. Why? I'll let you know it. So, as I told you, SO3 is the electrophile because sulfur has got partial positive charge because of the 3 oxygens that it is bonded. You know that oxygen is more electronegative than sulfur, and hence sulfur has got a partial positive. But this positive charge is not enough to attack the benzene ring. So, we say the electrophile character of SO3 is less and hence cannot attack the benzene ring directly. Now, what do? Like we have done in nitration, we have used the acid to enhance the electrophilic character of the electrophile. Same we do here. In chlorination and bromination, we have used Lewis acid, say AlCl3 or FeBr3 or strontium chloride, etc., to enhance the electrophilic character of the species. Here also we do the same. What do we use? We use here concentrated sulfuric acid. So what is happening here? I'll tell you. Sulfuric acid is this H2SO4. What does it do? It donates a proton. It donates a proton to SO3. Guys, you people know oxygen has lone pairs and is capable of accepting the proton. Now what do you have? You see, you have HSO4 minus. This is the species formed when sulfuric acid donates the proton. We call this as the conjugate base of sulfuric acid plus SO3 accepts the proton. It grabs the proton to give this. So you'd be getting this OH plus, this is what we have, O. Now guys, oxygen, which is the second most electronegative element in the periodic table, is not at all comfort with the positive charge. Then what does it do? Guys, it will try to gain the electron from this sulfur. Now we are going to get this, yes, O3, O3H. But there is a positive charge on the sulfur. Why? Because oxygen has accepted the electron. Is that point clear? Now the next step is same for every EAS reaction. That is the generation of the arenium carbocation and next the loss of the proton. So guys, what did I do? The partial positive sulfur has been converted into complete positive charge sulfur here. That means sulfur is more electrophilic now. Now what does it do? It attacks the benzene ring now. Am I right? So I'll show you what is happening in the next step. Guys, it attacks the benzene ring. Second step is the attack of the electrophile by the pi electrons of benzene. Am I right? So this benzene would donate the electrons to the sulfur. Right? Let us assume that the pi bond breaks like this. This carbon atom has got positive and this would get negative, which would be bonded to the sulfur. I just write as O3H. Yes, O3H. This pi electron has donated, benzene has donated the pi electron to the sulfur. As you all people know, there is even one hydrogen, in fact, on every carbon atom of the benzene ring. Is this clear? So this is the arenium carbocation that we have. So this is the electrophile and its character has been increased by this sulfuric acid. It attacks the benzene ring to give this arenium carbocation. Next is the deprotonation. Deprotonation is the process of removal of the proton. Now this hydrogen from this species, we call this as arenium carbocation, which is the RDS, rate determining step. Am I right? Very slow step. Am I right? Because the benzene ring has lost its aromatic character. It tries to regain its stability. How? By forming the ring. So you have 2 pi bonds, one more pi bond can be generated here. How? If this proton is lost as a H plus, this carbon gets positive charge and then there can be a pi bond formed, resulting in the aromatic ring. When this H plus is lost, you would be getting this species. Who is going to grab the proton? Guys, this is the base we have. I have taken HSO4 minus. This grabs the proton. What is the driving force for this? Formation of this stable aromatic compound. Clear? So HSO4 minus grabs this proton to give back this H2SO4. So the role of H2SO4 is just to act as a catalyst. Am I right? We are treating it, we are making it to increase the electrophilicity of the SO3, electrophile. Am I right? So this is how the reaction takes place. This is SO3H. Clear? So the role of the acid is to increase the electrophilicity of this SO3, right? Now guys, we have a bonus topic here. What is that? Sulfonation is reversible in nature. Why? Let us see. Guys, till now I have been discussing in every ES reaction that electrophile attacks the benzene ring, electrophile attacks the benzene ring. But guys, can you see this? Can a benzene ring be attacked by this proton? Because this is an electrophile, right? Can this attack? Of course it can, because this is electrophilic and this is nucleophilic. It has got pi electron cloud. Now what would happen if I add an H plus ion to this? Obviously, you expect the pi bond to be broken, right? Resulting in an arenium ion. This is what we have. But guys, can you see? This is highly stable and the reaction is so reversible that the reaction always takes place in backward and rarely proceeds in forward direction. So this rarely proceeds in the value of K for this reaction is very less, that the reaction never proceeds in forward direction. It always goes in the backward direction. Hence, we never considered this reaction to occur. It's very difficult for occur. Now, I considered the another case. What is that? So, since this is reversible, I didn't understand. Now, let me take this electrophile. I have taken the benzene ring and let me attack this with HSO3 plus. What is HSO3 plus? Just see guys, we have this, this. This is the RDS. I told you RDS reactions are, this is very difficult, a slow step and is the RDS. I'll just see this reaction now. What do I have? This is benzene that I have and I'm treating this. What is that you are going to get? You would be getting, a arenium carbocation. How? By the breaking of this pi bond. Right? You would be having one hydrogen, however, and you will be getting this. Am I right? Now the next step is the loss of proton. But guys, there is one more thing that can also occur. What is that? Can you see this? This HSO4 minus can also react with this HSO4 plus. Suppose if instead of hydrogen, if this is lost, what is lost? HSO3 plus is lost from the benzene aromatic arenium carbocation. Then what would happen? Of course, this carbon would get negative charge and resulting in benzene. This is a possible case. Plus, guys, you see, this HSO4 minus will react with this HSO3 plus. Like how? HSO4 minus grabs this proton to give H2SO4 plus. What is remaining here? It has lost the proton. What is remaining? SO3, sulfur trioxide. I need not remind you that sulfur trioxide is a gas and escapes out. Now the point is, according to Le-Chatelier principle, when a system is at equilibrium, removal of products will favor forward direction. Now the product is removed. So what is that you are going to get? You are going to get the forward reaction. Forward reaction is getting back benzene. I have my SO3 and H2SO4. SO3 escapes out and you are getting back the benzene. That means the reaction is reversible. We have got back the reactants. Hence, I told you at the beginning of the reaction that the reaction is reversible. This is also possible. No matter how slow the forward reaction is, when you keep on removing the product, the reaction keep on proceeding in forward direction. So guys, this is very important. That is the reason why this SO3H is used as a blocking reagent. We'll see how it is used in the synthesis of many other products in the next coming up sessions. Right? Guys, the question is here, sir, why didn't you consider the same reaction here in case of chlorine and this? Yes, you see, generally a strong bond is retained and a weak bond is broken. Am I right? You can't break this a strong bond between carbon and chlorine instead of this weak bond carbon. We generally, the reactions prefer this weak bond. Am I right? Even if the product is formed, it will come back and return and attack this, giving this species. But here that is not the case. Sir, why can't the reverse happen? The reverse can happen like in the other case. But the thing is, SO3 is a gas which is escaping out. So there is no backward reaction taking place. Instead, removal of product will favor backward reaction. So that is the thing that is happening. You can't say here, sir, Cl moves out from here as Cl plus. Yes, Cl plus will still be in the reaction mixture and it will again attack this to give back this one. Here that is not the case. The SO3 will escape out. So that is the reason SO3 is the electrophile, and I have used concentrated sulfuric acid which is always ready to attack it to convert into HSO3 plus. Am I right? So guys, this is the important part of this sulfonation. It is reversible in nature. You can bring back benzene and SO3 in the reaction mixture, right? And is used in the synthesis of many products that we'll be discussing in the coming up sessions, right? So guys, that's all we have in lecture number 3. This is the end of the concept. We have seen the electrophiles of different EAS reactions. In the next lecture, we'll be discussing about Friedel-Crafts reactions, right? That's all we have from Teach Tigers. Thank you. Have a nice day.